Right. So, now we come to the final section on the 2D edge based finite element method. So far we have looked at shape functions, weak form, boundary conditions and choice of formulation, total field or scattered field formulation. The final step is to show you how to put it all together into a system of equations. At the end of the day, we want Ax is equal to B, a linear system of equations which we can solve. Okay. So, let us try to put it together. So, what we will do is going to be very similar to what we did in the case of 1D FEM. What did we do? We took a line and we chopped it into elements and found out the system of equations. So, let us get into that. Okay. So, the minimum building unit to talk about this is going to be 2 elements, because an edge, except if it is on the boundary, will always be shared by 2 elements. Okay. So, let's draw that. So, these are 2 adjacent elements. Okay. Now, one very important thing to keep in mind in FEM in general is the mapping between global nodes to local nodes to global nodes. Okay. Not just nodes, now we are talking about edges, right. This is a edge based FEM. So, we also have to keep a table which allows me to go from a local edge to a global edge numbering. Okay. So, each of these I will use a different color for, let us use the color green for local. Okay. So, these are 2 elements, let us call this element A and let us call this element B. Okay. Each of these triangles has 3 nodes and there will be some local numbers. So, the local numbers of the nodes will be, for example, 0, 1, 2, 0, 1, 2. Okay. So, this node will be 0, 1, 2. Similarly, I can say that 0, 1, 2. These are the local nodes. So, let us be very clear, what determines which one is 0, which one is 1, which one is 2? Is there anything sacred about which is 0, 1 or 2? No, these are node numbers, we are only talking about node numbers, there is nothing sacred whatsoever. So, how do I fix which is 0, 1, 2? You can choose it any way you want, but in practice you will not get to choose it any way you want. The software which meshes the domain will give you a list of, for each element it will give you a list of nodes. So, it will list it will list the 3 nodes in some order. So, you will choose the first one to be 0, second one to be 1, third one to be 2. Okay. So, this is coming to you from the mesh, from the CAD software which you will use to mesh the domain. Okay. So, it's sort of given to you, but there is nothing very sacred about it, right. You could remap it if you really wanted to. Well, the meshing software may internally try to follow a convention of clockwise, but clockwise still will not tell you where on the clock you are starting. Are you starting at 6 o'clock, 12 o'clock, 9 o'clock? Right? So, and it may violate that convention also. It's not, so we shouldn't count or depend on any particular convention. We just want the 3 nodes, right. Now, corresponding to these local node numbers, I get to choose how to fix the global node numbers. Okay. Because once I start reading in, I will see if there is any node being repeated. I will not give a new number to it, right. So, that is the part of code which I have to write. So, let us call this guy global node number 1, global node 2, global node 3 and global node 4. Okay. Yeah, 2, as let us say when I read in the CAD file, it will give me element A, element B and the nodes for element A and the nodes for element B, but 2 nodes are common. So, I should not double count when I am doing the global numbering, that is all. Okay. So, if we were doing a node based FEM, we would stop here, but we are not doing a node based FEM, we are doing an edge based FEM. So, the next thing to take into account is the edges, right. So, edges, let us see how to do. So, there are many conventions. One convention simply is in the following way: from smaller local node number to greater local node number, right. That could be one convention, it is up to you. So, for example, these can be, I will call this local edge number 0, local edge number 1, local edge number 2. Okay, it's up to you how you define it, but you because you're going to code it, you need some logic, right? So the logic can just be this, right? The next is over here, and over here. Yeah, so the natural question will come, how do you fix the continuity equation, right? So these are, as I told you, these are local node numbers, local edge numbers, and there is a one-to-one mapping to unique edge number. So it seems that this edge between node 2 and 4 has the vectors in the opposite direction, but that can be fixed by taking care of this local to global. We will see how it happens. Okay. So we have fixed the local edges. What remains is global edges, right? So the edges need some kind of a unique thing, right? So I can say edge number 1 is this, edge number 2 is this, edge number 3 is here, and edge number 4 comes here, and finally I have edge number 5. Okay, these are, so let's write this over here, these are global yeah. So now just as I had a convention for local edges, that let us say from smaller node number to larger node number, similarly I can have a convention for the direction in which a global edge should point. So I can say that global edge number 1 is from smaller global node number to larger global node number. So this edge, for example, can be assigned to be pointing in this way, this can be assigned to be pointing in this way, similarly in this way, and then this can be, this will end up being this way, and 5 will be from 2 to 4. Okay. So the only thing I have to take care of is that on a common edge, if the global and the local edges differ by a direction, then I have to add a minus sign in the equations. Because the convention I have taken is convention edge points from smaller number to larger number. So you see this edge number 4 is pointing from global node number 1 to global node number 4. The direction is from smaller number to larger number.
So in 2 to 0 there is one local edge, right?
2 to 0, there is no 0 number over here in terms of the global nodes. Okay. Is this part clear? So these are the things which you have to be very careful about when you code. There is a set of global conventions and a set of local conventions and a one-to-one mapping over here. So 5 is pointing from 2 to 4. Okay. When I talk about global edges, the convention comes from global node numbers. When I talk about local edges, the convention comes from local node numbers. Okay. So all of this you didn't have to really worry about that much when you did integral equation methods. Here it's important to do this. Okay, very good. The next thing is, I mean, so far when we looked at the boundary conditions and the total field versus scattered field formulation, we were paying a lot of attention to the right hand side. But now it's time to also take a look at the left hand side, right. So the left hand side term, which appears again and again, is of this form, right. So there was a curl of T dot 1 by epsilon r curl of H, right, minus mu r k naught square T dot H. So this was the left hand side term. Okay. So now this expression will keeps appearing again and again when I look at element A, element B and so on. So I am going to write a shortcut for this. Okay. I am going to call this capital phi of T comma H. just a shortcut. So, when you see capital phi of t comma h, I mean this expression. So, what is the FEM procedure to get a system of equations? Take 1 t. So, supposing this very simplistic example of just 2 elements, supposing my mesh was just made out of 2 elements, then how many edges do I have in total? 5 edges, right? And I could take the testing function to be each one of the edges, the shape function corresponding to each edge, and get 5 equations in 5 variables, right? So, that is going to be the general procedure. So, let us just take let us try to derive the system of equations I get if I do testing with using edge number 5. Right. So, now testing with, let me say not with but along and when I say edge 5, obviously I am referring to the global edge number 5. Okay. Now, edge number 5 is shared, the reason I have taken 5 is because it is more interesting, it is common to both the elements, right. So, again like in 1D case, I had a choice whether the basis function should be belonging only to one element or linear combination of something that belongs to both elements, right. Here also we will do the same thing. My testing function is going to be the sum of the basis function corresponding to element A and element B, right. It is like that triangle function which I had in 1D, right. So, this is non-zero over element A and element B. So, you can think of it as, supposing I wanted to use the convention. So, T belonging to which element now? Say element A, and local edge number what? 2 plus T of element B, local edge number 2, right. So, this is my
what about that plus sign? That direction is not significant here because since you are using local edge.
It does not. So, the question is that these two functions Ta2 and Tb2, they have a different sign on the edge. It will not matter. It will, I mean, I will get a minus sign in the system of equations. Okay. So, once again I must mention that I could go in a slightly slower manner. I could just take Ta2 once, get one equation. Take Tb2 once, get another equation. Okay. This is like a shortcut that we will do. We will take it at the same time. Okay. No, these are, well, this is a testing function. So, yeah, T2a, T2b, yeah, because I have to make the testing function as a composite sum of two things. So, there I have to somewhere refer to the local things, right. The reason I am doing this is because we said there are 5 global edges. So, there will be 5 variables. So, I should get 5 equations. How many local local triangles are there? 6 are there, right. So, I will get one extra equation. I will get 6 equations in 5 variables. To avoid that, I have combined these two. Okay. All right. So, now let us see what happens when I take my weak form. So, everyone is, let us go back to our weak form over here, right. Further still, yeah, here is the weak form, right. This is the left hand side and the right hand side is that contour integral. Okay. So, let us just come back to this. TB0, not TB0, TB2 we can take. 2, so in element B, edge number 2 corresponds to global edge number 5, right. No, right now I am not naming it by the opposite node number. There are various conventions. You can choose whichever convention you want. Here I have taken that the global edge number, the local edge number corresponds to the starting local edge number, like, okay. And I have taken a slightly different convention from earlier because various reference books have different conventions. So you shouldn't think that there is some universal agreement on how to number these things. Fine.